Okay, hello everybody to today's ISGC seminar talk. It's a very big pleasure for me now, to introduce you my former PhD advisor, Volker Perlick. He did his PhD in 1989 at the Technical University of Berlin, and then he also did his habilitation there. And since in 2013, he then transferred his habilitation to the University of Bremen. And although he's officially already retired, he's still very active in science, and he will present today his work with Oleg Tsupko on gravitational lensing in the plasma on the Kerr spacetime. And with that, I hand over to Volker. Thank you very much for giving this talk. The stage is yours.
Yeah, thank you very much for the invitation. Good evening or good morning or whatever time it is at your place to all of you. So what I want to talk about today is essentially the content of a paper which appeared recently in PRD. It's a paper together with Oleg Tsupko. And we made it part 2, which is unusual for PRD actually. They don't like this usually, but in this case, they allowed us to name this paper part 2. And actually, it's very natural because it's a very close follow-up of an earlier paper, which appeared already in 2017. In this earlier paper, we asked and answered the question, under what condition is for light rays in a plasma the equation of motion separable? So under what condition do we have an additional constant of motion so that we can reduce the equations of motion to first order? I guess most of you know that this is possible for vacuum light rays because there's the so-called Kerr constant. And the question which we discussed in this first paper is the question, under what condition do we also have a generalized Kerr constant for light propagation in the plasma? And based on that, we could then do several things analytically for light rays in the plasma, which could not have been done analytically without this constants of motion. And we followed up on this work in the second paper, so we added some new aspects and some new results, and that's what I'm going to talk about today. So, why is my screen not moving? I wanted to, here, okay. So I organized this talk in the following way. I want to begin with telling you quite generally how we describe light propagation in the plasma. When I say plasma, I should say, I mean the simplest model of the plasma. It's a non-magnetized plasma, and it is what is sometimes called a cold plasma, which means that the pressure can be neglected. That's the simplest model of a plasma you can think of. And I will tell you in the first part how you treat this kind of light propagation in general on an arbitrary spacetime. And then I will specify to the Kerr spacetime. I will give you this result on the separability condition. And on the basis of this, I will then discuss a shadow in a plasma. Before that, I will briefly remind you how the shadow is constructed in vacuum, for vacuum light rays. I will then present to you a bending angle formula for light rays in a plasma, a new one. And in the last part, I will briefly address the rather, intriguing fact that in a plasma you can actually have circular light rays off the equatorial plane. That's something which does not exist for vacuum light rays, at least not outside of the horizon of a Kerr spacetime. And when I speak about the shadow, I want to give as a general reference for how to calculate shadows in black hole spacetimes and spacetimes of other compact objects. I want to refer to my review article, again together with Oleg Tsupko, which appeared 2 years ago in Physics Reports. Okay, how do we describe light propagation in a plasma? And as I said, I will restrict to this case of a non-magnetized and pressure-free plasma. And we assume that this consists of ions and of electrons. So actually the formalism which I want to talk about is not valid for an electron-positron plasma, because it's really used in the derivation of the equations that the positively charged particles are much more inert than the negatively charged ones. So you should think of an electron-ion plasma. And in this case, it was derived many years ago that the light rays can be written as a solution of Hamilton's equations with an appropriately chosen Hamiltonian. So Hamilton's equations, which are written here in the first blue line, I think they are familiar to all of you. It's exactly the form which you learn in your first course on classical mechanics. The only difference is here that the index I takes values 0, 1, 2, 3, because we are in a four-dimensional space-time. And the Hamiltonian, which you have to choose for light rays in a plasma, is the one which is written here in the second blue line. So if this omega p is 0, then this is just the Hamiltonian for the geodesics. And because I want to have the solution with h equals 0, it's the equations for light-like geodesics. With the omega p, it's the equation for light rays in a plasma, and the omega p is the so-called plasma frequency. So this is essentially the electron density. Yeah, in front of the number density of the electrons, there are constants of nature: the electron charge, the electron mass, and the permeability. The permittivity of vacuum in SI units. So when we are in a plasma, then we have a positive omega p, and then the equations of motion have to be written down with this modified Hamiltonian. So the light rays will then deviate from light-like geodesics. So this Hamiltonian formalism does not come out of thin air. It was actually derived, rigorously derived from Maxwell's equations with a two-fluid model for the plasma for the first time by Breuer and Ehlers in 1980. So I say it was for the first time rigorously derived because there are earlier papers on that. But I think Breuer and Ehlers were the first who did it really rigorously on a curved spacetime, on an arbitrary general relativistic spacetime. And they even did it for a magnetized plasma. Then the Hamiltonian is much more complicated. It's actually given by an eighth order polynomial in the momenta. And it's anisotropic. So particular spatial directions are distinguished from other ones. Obviously, the direction of the magnetic field distinguishes a direction. So this is much more complicated. If you are only interested in the non-magnetized case, then you can find the derivation of this Hamiltonian formalism also in my book from the year 2000. Okay, I've written here the equations again. And what you read from these equations, look at if you insert the Hamiltonian in the equations for xi, in the equation for xi dot in the first equation, then you see that the xi dots are just the pj's with an index pulled up. And if you look at the third equation, h equals 0, you see then if you replace the pj's by the xi dots, that Gij xi dot xj dot is just the negative square of the plasma density. So Gij xi dot xj dot is always negative if you are in a plasma. This means that the light rays are time-lag curves. Yeah, in vacuum they are light-lag curves, light-lag geodesics, but in a plasma they are time-lag curves. So the light rays move at a speed slower than the speed of light. And actually, if you look a little bit more closer at the formalism, you see that light rays are time-lag geodesics of a conformally rescaled metric. Namely, if you multiply the metric with omega p to the power minus 2, then you get a conformally rescaled metric, and the light rays in the plasma are time-lag geodesics of this rescaled metric. Maybe you are more familiar with formalism of light in the plasma in a 3+1 formalism. You might have heard about this in one of your university courses. And you can reach this 3+1 formalism by choosing an observer field. Yeah, an arbitrary vector field which is time-lag, normalized to minus c squared. So the world lines of these, the integral curves of this vector field can be interpreted as the world lines of observers. And with respect to this UI, we can then decompose the momenta, the PIs, into a temporal part, temporal with respect to ui, and the space-like part. And the temporal part gives the frequency, omega, and the space-like part gives the wave covector, ki. And then the equation h equals 0, that's what's usually called the dispersion relation. This equation becomes can be solved for omega, for the frequency. And it says that omega is the square root of c squared k squared plus omega p squared. Maybe you have seen this equation in this form. So that's the dispersion relation in 3+1 form, in the equation which relates the wave covector to the frequency. If you have the dispersion relation in this form, then you can, according to standard textbook procedure, derive the phase velocity. The phase velocity is just omega divided by k. And you see in this case, it is always bigger than c, because under the square root you have something where a positive quantity is subtracted from omega squared. So you get something with a square root which is smaller than omega. So the entire expression is bigger than c. But this should not be a reason for worry, because the phase velocity, as you probably know, is not associated with a signal. So there are many kinds of media for which the phase velocity is bigger than c, and this is no reason for concern. Actually, the group velocity, the omega by decay, this is actually smaller than c. If you have the phase velocity, you can define an index of refraction. It's defined as a quotient of the vacuum speed of light divided by the phase velocity. And you see the index of refraction in the plasma is always smaller than 1. So here I've written the expression for the index of refraction again, because you can read a couple of things from that. The first observation we made is that propagation is possible only if omega is smaller than omega p, because otherwise we would have a negative quantity under the square root, which is of course nonsense. It doesn't give a valid propagation for light. Actually, in this case, if omega is smaller than omega p, then actually the light ray would just get stuck. It would not be able to propagate in a medium, in this medium. Actually, that's what happens if you send a light ray with a certain low frequency upwards here on Earth, then it will be reflected at the ionosphere, because the plasma density in the ionosphere is then bigger than the frequency. So the ray would just bounce back. Okay, first observation is omega must be bigger than omega p at each point of space-time. Second observation is, if omega is much bigger than omega p, then you can neglect this quotient, omega p squared divided by omega squared, in comparison to 1. And the influence of the plasma is negligible. Yeah, then you have n approximately equal to 1, which means that you have light propagation approximately in the same way as in vacuum. So the interesting case where we really, when we do light propagation in a plasma, the interesting case is that the plasma frequency is the frequency at which we observe is bigger than omega p, but not much bigger. And now let's have a look at a few plasma densities in the universe. So the solar corona, for instance, near the solar rim, has a plasma density of about 100 megahertz. The ionosphere about 10 megahertz. Interstellar space is about 10 kilohertz, and intergalactic space is 10 hertz, which is extremely, extremely low, very, very long wavelengths. So you see that the question of the program of discussing light propagation in a plasma is relevant only in the radio. Yeah. So if we are in the optical regime, or even in ultraviolet or X-ray, then the influence of the plasma is always negligible in all practical cases. Well, I am particularly interested in the environment of black holes, and we don't know exactly how big a plasma density can be near a black hole, but probably it will not be bigger by several orders of magnitude than in the solar corona. So I would guess that it is maybe 2 orders of magnitude bigger than in the solar corona, but not more than that. So we are still in the radio. So whatever I tell you now in the following is relevant only for radio rays. Okay, so this was a general formalism for an arbitrary spacetime. Now let's specify to the Kerr spacetime, and in particular address this problem of separability. So here in this blue equation, I've written for you the Kerr metric, which I guess is a good friend for many of you. So it involves 2 parameters, a mass parameter m and a spin parameter a. Both have the dimension of a length. And I'm particularly interested in the case that m squared is bigger or equal than a squared, so that we have a black hole. Otherwise, we would have a naked singularity. But I'm mainly interested in the black hole case. And there are these 2 common abbreviations which will occur in all the following equations, the delta and the rho. The delta is a function of the radius coordinate r alone, and the rho is a function of r and theta. So this is something you should keep in mind. And now we assume that we have on the Kerr metric a plasma density, and we assume that this depends only on r and theta, which means that it shares the symmetry of the background spacetime. Yeah, the Kerr metric is a stationary spacetime, so there's no t dependence, and it is an axisymmetric spacetime. There's no phi dependence of the metric coefficients, and we assume the same thing for the plasma density. So the entire system is stationary and axisymmetric. And then we have obviously 3 constants of motion. Namely the Hamiltonian, which is always a constant of motion, it is 0. Then the momentum p phi, which is associated with the Killing vector field d by d phi, and the momentum coordinate pt, which is associated with the Killing vector field d by dt. And the latter one is, in particular, if we are talking about light propagation in a plasma, it's convenient to divide it by c and embellish by a minus sign. And to call this omega naught, this is then the frequency constant of the light which we are considering. It's not the frequency which actually an observer observes somewhere. It is a frequency constant. Yeah, it's a constant of motion. And if you look at the equations more closely, you will see that for a light ray that reaches infinity, it is actually the frequency at infinity as measured by a stationary observer. So that's the meaning of this constant omega naught. So you should be clear about the fact that it's not the frequency along the light ray which is changing in general. Yeah, there's something like gravitational redshift. The omega naught is a constant of motion. It's constant along the light ray, and it has a meaning which I explained to you. Okay, so we have 3 constants of motion, but we are in a 4-dimensional spacetime. So we need another one for what is called a complete integrability of the equations. So we need another constants of motion. And in vacuum, it is well known that such an additional constant of motion exists. It's called the Carter constant. It was found by Brendan Carter in 1968. And the question which we investigated in the first paper was under which condition also the light rays in a plasma emit. So they're given now by this set of Hamilton's equations. Yeah, we discuss this set of Hamilton's equations, and we ask, is there another constant of motion? And the answer is yes, provided that the plasma density has a particular form. It must have this form here. It must be an arbitrary function of r plus an arbitrary function of theta divided by r squared plus a squared cosine squared theta. If the plasma density does not have this form, so for instance, if we are in a Kerr spacetime with a different from 0, so it's really a spinning black hole which we have, and we consider a plasma density which depends only on r, then you see that it does not have this form unless it is a constant. Yeah, we really need a theta dependence on the spacetime of a spinning black hole in order to have this separability condition satisfied. In the Schwarzschild case with a equals 0, actually the separability condition is obviously satisfied if the plasma density is spherically symmetric. That's a sufficient, not a necessary, but a sufficient condition. So yeah, and actually, if you want to see a derivation, a proof of this equivalence, which I've written here, then I have to refer you to this this first paper from the year 2017, which I mentioned. Actually, in the meantime, we have also generalized this result to an arbitrary stationary and axisymmetric metric. So in this paper with Oleg from 2017, we considered only the Kerr spacetime. But in this more recent paper with Barbara Betsikova and Yuji Bichak, we asked the same question for an arbitrary stationary and axisymmetric metric. And we gave the criterion for separability in this paper here, which I quote here on this page. In this talk, I will restrict to the Kerr metric, but if you are interested in the more general results, then you may look it up in this paper. So now I assume that the separability condition holds. So we assume that we have a plasma density which is of this particular form. Then we can reduce the equation of motion to first order form. That's what one calls complete integrability. Or some people say integrability in the sense of Liouville. So we have equations for T dot, for phi dot, for theta dot, and for R dot. And the important thing that comes from the separability, from the existence of this Carter constants, which I denote K. If you look at the equation for theta dot and for R dot, you see that on the right-hand side, you have only a function of theta in the first case and only a function of R in the second case. And this is what comes out of this separability result. And on the basis of this result, we can now ask for so-called spherical light rays. This is a crucial question which we have to answer if we want to discuss a shadow. So I'm now approaching the issue of the shadow in a plasma. And for that, I have to investigate the spherical light rays. Actually, linguistically, this is a strange word, I have to admit, but yeah, it got stuck now. So we speak of spherical light rays if we mean that we have a light ray which is contained in a sphere R equal constant. Yeah, a coordinate sphere R equal constant. So then obviously, if you look at the last of the four equations of motion, then obviously because the little r dot and the little r double dot must then be both 0, which means that the capital R must be 0 and the derivative capital R prime must be 0. And then if you look at the third equation, you see that on the left-hand side you have a square. So what I call capital theta of theta cannot be negative. So this is an inequality. So you have for spherical light rays 2 equations and an inequality. The 2 equations can be used to eliminate the constants of motion k and p phi. And then the inequality gives you the region in space-time where these spherical light rays exist. And that's what I call the photon region. And if you do the algebra, you get this inequality here. So you see it's an inequality. So it determines a region in space-time, yeah, where this inequality is satisfied. And through each point of this region, you have a spherical light ray. And then you have a plus-minus sign. And actually, this condition can hold with a plus sign and with a minus sign, which means that it's possible that there are 2 different spherical light rays to a particular point in space-time. In vacuum, this considerably simplifies. Vacuum means the FR is 0 and the F theta is 0. And then you see that this plus-minus sign doesn't survive, only the plus sign survives. The condition can never hold with a minus sign. So you get the condition which is here written in the lower part of the screen. And actually, yeah, this inequality for the existence of spherical vacuum light rays, this yeah, can be found, for instance, in my living review from 2004. And but in a medium, in a plasma, it's considerably more complicated. And the most essential new feature is the occurrence of this plus-minus sign, which actually makes the analysis yeah, a little bit more yeah, subtle. Okay, so that's the photon region. And I will show you now a few pictures of this photon region, first for vacuum. So I will now approach the notion of the shadow in vacuum. And to that end, I will first talk about the photon region for a Kerr black hole in vacuum. So I assume here that the spin parameter is 0.75 m. So the black hole is, it's rotating fast, rather fast, but it's not yet extremal. And then the photon region is this blue region here. So everything is rotationally symmetric around the z-axis. Yeah, so what I've shown here is a meridional cross-section, a vertical cross-section through this situation. So there are two horizons. So the region between the two horizons is shown here in black. What is inside the inner horizon is for us of no interest. And for this reason, I've shown the photon region only outside of the outer horizon. And there it is this, this shell-like structure. Yeah, it's something like, no, it's not a torus. It's it's a shell. It's a shell. And so each point of this shell, I have a spherical light-like geodesic. This means a geodesic, which sorry, not I'm in vacuum. So at the moment I'm talking about light-like geodesics. So I have a light-like geodesic through each point of the blue region, which stays on a sphere r equals 0. So here is one of them. Yeah. So you see, this is in this cross section, this is just staying on a circle. But actually, there's also a phi motion, an azimuthal motion, and this can be rather complicated. Yeah. So these spherical light-like geodesics can even turn back. So they go for a certain time in the positive phi direction, and then they turn back and go in the negative phi direction. That's possible. Inside the ergo region, something like that is possible. So each point of the blue region, I have such a light-like geodesic. So they are in general not circular. They stay on a sphere, but they are not circular. There are only two circular ones. One is here at the outermost point. This is actually a counter-rotating circular light ray. I think most of you are familiar with the existence of this circular light ray. And there's another circular one. Sorry, that was the wrong direction here. It's the innermost point in the equatorial plane. So this is a co-rotating circular light-like geodesic. Yeah, these are the only ones which are circular. All the other ones are spherical but non-circular. So for instance, there's one which goes through the axis. This is also not circular because there's a precession in the phi direction. Yeah, so it it's doing some kind of how to call it? Yeah, it's precessing. It's precessing in the phi direction. So, and now I want to, why is this photon region interesting? It's interesting because it's crucial for the construction of the shadow. So when we ask about the shadow, we do the following. We fix an observer somewhere outside of the horizon, but otherwise anywhere you like. It may be very close actually to the black hole, but outside of the horizon. And from this observer position now, we construct all light rays which go from this event into the past, or to put this another way, which arrived at this event. So all light rays which the observer can actually see. And here in this case, in the vacuum, for vacuum light rays in the Kerr spacetime, they're divided into two classes. One class is light rays that go to the horizon, and the other class is light rays that go to infinity. And the borderline between these two classes is light rays which spiral towards one of these light rays in the photon sphere. And for that to be possible, it's crucial that all these light rays in this photon sphere here, in this photon region, are unstable. Yeah, otherwise, a light ray could not spiral towards it. So they are unstable. So if you perturb it a little bit in the radial direction, then it will actually go away from the sphere on which it lives. So these unstable light rays can serve as limits for other light rays which come from some other point from the observer position. So we have two classes of light rays, the ones which go to horizon, the ones which go to infinity, and the borderline cases which spiral towards the photon region. And what has this to do with the shadow? Now, we get the shadow from this construction if we assume that we have light rays anywhere in the spacetime, but not between the observer and the black hole. Yeah, in the region where the light rays go through, which go to the horizon. If this condition is satisfied, if we have light rays only, not in this region between the observer and the black hole, then we would assign darkness to all light rays which go to the black hole. To the other one, we would assign brightness because they meet one of our light sources. So what the observer sees in the sky is a region which corresponds to the directions of light rays which go to the horizon, which is black, and it's surrounded by a bright region. And how do you construct this, how do you translate this construction into mathematics? Well, the first thing we'd have to do is we choose a tetrad at the observer position. So we have an observer at rho theta O, somewhere outside of the horizon, arbitrary r coordinate, arbitrary theta coordinate, and there we introduce an orthonormal tetrad, E0, E1, E2, E3. You see the E3 is chosen in the sense that it points towards the black hole. Yeah, it goes in the negative r direction. So the E3 is, if you have the black hole above your head, then it means that the 3 coordinate is a vertical coordinate. Yeah. And now if we introduce celestial coordinates, if we coordinatize the sky of the observer with usual spherical coordinates, which I denote theta, not var theta, theta. Yeah, we have to distinguish it from the spacetime coordinate var theta. So the celestial coordinates are theta and psi, and they are defined with respect to this tetrad by the equation which I've written here at the bottom. So if I have a tangent vector to a light ray, which is tangent at the point where the observer sits to the light ray, then I associate celestial coordinates theta and psi to this by this equation. And the theta coordinate by construction is a coordinate with respect to the direction to the black hole. Yeah. So if the black hole is exactly above your head, then the theta coordinate is the usual how it is called latitudinal coordinate. Yeah. Okay, we have now coordinatized the sky of the observer, and now we have to find out those light rays which go to the horizon. That will be the ones which are associated with darkness, and the boundary of this dark disk is then characterized by light rays which spiral towards the photon region. And the first thing we have to do in order to work this out is we have to associate the celestial coordinates psi and theta with the corresponding constants of motion, k and p phi, and omega naught. These are our constants of motion. And this can be done with the help of the equations of motion, by calculation of a few lines. And this is a result here for the vacuum case. And now we have to single out those light rays which spiral towards the photon sphere. These are the ones which have the same constants of motion as the ones I said photon sphere. Sorry, I meant photon region. It's not a sphere. So we have to single out those constants of motion, which, or those light rays, which spiral towards the photon region, and they must have the same constants of motion as the constants of motion of the limiting light ray. Because if two light rays become tangential to each other, then they must have the same constants of motion, k and p phi. So we have to calculate the constants of motion, p phi and k, for the spherical light rays. And this is done here in the two equations at the bottom. This is, there's on the right-hand side a parameter r. That's the radius coordinate of the limiting light ray. So if we insert these expressions for p phi and k, and let the r run over all values for which we have spherical light rays, then we get psi and theta. We get a curve on the sky, psi of r, theta of r, parametrized with this radius r. So we get a fully analytical parametric equation for the boundary curve of the shadow. And this is what was first done not only for the Kerr metric, but for a bigger class of metrics by a PhD student of us by the name of Arne Grenzebach. And it was published in this paper here. So this is the shadow in vacuum. The equations that I've shown here to you, they are valid for vacuum. Actually, in vacuum, the omega naught drops out. Yeah, if you insert A and P phi and K into the preceding two equations, the omega naught will drop out. So the shadow in vacuum is frequency independent. And yeah, if you plot the boundary curve of the shadow, you get these familiar pictures. I think you have all seen pictures of this kind. So this is here for an extremal black hole. A is equal to m. And in the first picture, the observer is in the equatorial plane. Then you see this characteristic flattening on one side, which is an effect of the dragging of light rays. Here the black hole is spinning. On one side, it drags the light rays with itself. On the other side, the light ray has to act against the dragging. So this produces this asymmetry. If the observer looks at a certain angle, on a certain inclination, then the shadow becomes rounder and rounder. And if you look exactly from the top or exactly from the bottom, the shadow is circular. And needless to say, the shadow of a black hole or a black hole candidate has been observed by the Event Horizon Telescope collaboration. Actually, not only one, actually only also for two, even for two candidates, the one at the center of our galaxy and the one at the center of M87. And in both cases, yes, the observations seem to indicate that we are looking from the top or from the bottom. So the spin can actually not be read from the shape of the shadow. So this was the vacuum case. Now let's come to the plasma case. You can do exactly or analogously the same thing, provided that the separability condition hold. We do exactly we proceed in exactly the same way. We choose the same tetrad. We introduce the same celestial coordinates. And now we have to evaluate these modified equations of motion, the equations of motion with this functions fr and f theta. And this gives more complicated expressions for psi and theta, and also more complicated relations between p phi and k and the angles in the sky. And yeah, here are the relevant equations. It's still fully analytic. Yeah, so you can get the light rays which spiral towards spherical geodesics from these equations in analytic form, and this gives you a curve in the sky. And I show you now an example. This is for a constant plasma density, which is physically maybe not so very much interesting, but nonetheless, it's something which you can consider as an illustrative example of the methodology. And now you see there are some interesting new features as you compare this with a vacuum case. So actually, I've chosen here the omega c. So we have a plasma density which is constant. This constant is called omega c. The black hole is extremal now in this case, A equal m. And then I have to tell you what the omega naught is, because now in the plasma, the light propagation depends on the frequency. And I have chosen here now a frequency which is, or let me put it the other way around. I've chosen a plasma density, which is pretty big. Yeah, so the quotient is bigger than 1 here. This means that for big radii, where the omega naught is a frequency, which is observed by stationary observers, that at big radii, the light rays cannot propagate. And that's what I've indicated here by this crosshatched region. In this region, light rays with this frequency constant omega cannot enter. So if they arrive at the boundary of this crosshatched region from the interior, they are bouncing back. Yeah, they are reflected. So that's the first new feature, that we have a forbidden region for light rays. The second new feature is that we have not only unstable spherical light-like geodesics, we have also stable ones. So the stable ones are here shown in green and hatched, the region where they live. And the other ones are the orange ones, the unstable ones. So light rays can spiral towards light rays in this orange region. They cannot spiral towards light rays in the green region, but they can oscillate about light rays in the green region, because there we have stable light rays. And if you now proceed, just mechanically, so to speak, as in the preceding case, you would say, let's construct the curve which corresponds on the sky of the observer, which corresponds to light rays that spiral towards the unstable photon orbits. And what you get is this here. So here I show you this for different ratios of omega c divided by omega naught. So if the omega c is 0, if we are in vacuum, then we get this red thing here. So that's a vacuum shadow. Then if you make the plasma density, if you introduce a plasma density and make it bigger and bigger, you first get the green one here, and then something very funny happens. Then the thing breaks open, and we get these fish tails. That's a blue curve here. And if you make the plasma even denser, then yeah, the whole thing folds over. We get this this magenta curve, and then even the black curve. But now the outer region of the curve is dark and the inner region is bright. Yeah. And when we arrived at this observation, oh, sorry, I jumped ahead. When we arrived at this observation, we asked ourselves, can these fishtail shadows really be observed? This is really something which can be observed. And for that, you have to now be very specific where the light sources are. So in the preceding case, in the vacuum case, we had only two types of light rays generically, and the borderline case in between. The two generic cases were light rays that go to the horizon and light rays that go to infinity. Here we have something additional. We have light rays that oscillates around stable light orbits. Also, we have light rays which bounce back from the here from this boundary of the crosshatch region, which cannot go to infinity. So these new features now makes it necessary to be very specific on where light sources are. And I think the natural assumption is that we have light sources, yeah, at big radii, but not at radii where these stable light orbits exist. So we assume that we have light sources distributed here at big radii inside the crosshead, not where the crosshead region is, but at smaller radii, but also not at radii where the stable light-like orbits exist. And if you then construct a shadow curve in the for these parameter values where you have these fishtails, you actually get that the fishtails are not observed. What is observed is a shadow, which is very similar as far as the qualitative features are concerned as the vacuum case. So actually, we believe now that these fishtails cannot be observed. So that was what I wanted to say about the shadow. Now let's talk about the bending angle. So if we talk about the bending angle in the Kerr spacetime, we should restrict to light rays in the equatorial plane. I would say that the very notion of a bending angle is not defined for other light rays, which are not contained in the plane. So the first question we have to ask is, do there exist light rays in the equatorial plane? And the necessary and sufficient condition is that this expression here has to hold, that the theta derivative of the plasma density at the equatorial plane is 0. So this is certainly true if the plasma density is symmetric with respect to the equatorial plane, but it's also true in other cases. So let's assume that this is satisfied. Then we have light rays in the equatorial plane, and we can consider a light ray which comes in from infinity, goes through a minimum radius r, and then goes back to infinity. And such a light ray would sweep out an azimuthal angle interval delta phi. And if we subtract pi from this delta phi, then we get this angle, which I've denoted delta here in this picture, and that's what we call the bending angle or deflection angle. And in a plasma, there's actually, we derived in our second paper a formula for this bending angle. We wrote it as an integral over a function f of r. And this function f of r is given here. Looks a little bit complicated, but it's quite explicit. Yeah. So what you prescribe is a minimum radius, capital R. So if the capital R is given, should of course be bigger than the horizon radius. So the light ray stays outside of the horizon, of course. So then we can write down this function f of r. If it's then quite explicit. And if we integrate it over the interval from r to infinity 2 times, then we get the bending angle. Here are a few plots. The first plot is for Schwarzschild. So the underlying spacetime is Schwarzschild. The solid line is for vacuum light rays. The white dashed curve is for a certain plasma density, and the narrow dashed is for an even higher plasma density. What you observe is the following. So for the vacuum, the bending angle diverges at r equals 3m. So this means that the light ray spirals towards the photon sphere, which in Schwarzschild is at r equals 3m. Yeah. So in Schwarzschild, what we had in the Kerr spacetime, we had a photon region. In the Schwarzschild spacetime, it reduces to the sphere r equals 3m. And this at this sphere, the bending angle diverges. If you now are in the plasma, then the first observation you make is that the limiting case is at a different r value. So the photon sphere is now at a different value. And you see that the delta phi becomes smaller than pi in a certain region, which means that the delta, the bending angle, is negative. What does that mean? It means that the ray is not attracted by the black hole. Yeah, when it passes by the black hole, it's not deflected in the direction towards the black hole. It's deflected in the other direction. So in a sense, it is repelled by the black hole. So this is something which is possible in the plasma. And if the plasma density is really high, as is true for the narrow dashed curve, then something even more specific happens. Then the delta phi could go to 0. What does that mean? It means that the light ray goes back to the direction from which it came. Yeah, it reaches this minimum radius, in this case here, phi 4m, and then it bounces back. It goes back in exactly the same path from which it came. So this could also happen in the neighborhood of a black hole. There could happen exactly the same thing which happens at our ionosphere. Yeah, I mentioned this already. If you send a light ray up or a radio ray upwards of a sufficiently low frequency, sufficiently big wavelengths, then it might bounce back from the ionosphere. And here the light ray is bouncing back from the black hole. So this is possible in a plasma around the Schwarzschild black hole and also around the Kerr black hole. The second picture refers to a Kerr black hole, a Kerr spacetime with A equal m, an extremal Kerr spacetime. And there are now plasma densities which fall off with different powers of r. So the solid line is for vacuum. The white dashed is for a fall off with the third power of r. The dotted for the second power with r, and the narrow dashed with r half. And you see that first of all, we now have to distinguish the co-rotating from the counter-rotating case. Yeah, so if the light ray moves in positive phi direction or a negative phi direction, this makes a difference. In one case, it's dragged along by the black hole. In the other case, it has to work against the dragging by the black hole. So you have, in one case, it's positive delta phi, in the other case, it's negative delta phi, and the situation is not symmetric. That's the first observation which we make. So the counter-rotating light rays, they stay farther away from the center than the co-rotating ones. And then we have a certain non-monotonicity. Yeah, if you look at the values for which delta phi diverges, then you see that this is actually, so there's a crossing over of these curves. So there's actually a non-monotonicity. So depending on the way in which the plasma density falls off. So that's another interesting feature which can happen in a plasma. Okay, and the last thing I want to talk about, that's the last section of my talk, is about circular light rays and possibly off the equatorial plane. So for vacuum light rays, in the Kerr spacetime, we have outside of the horizon 2 light-like circular geodesics, and both are in the equatorial plane. One is counter-rotating, one is co-rotating. In the Schwarzschild spacetime, we have the one at r equals 3m. Yeah, it can go in positive phi direction or negative phi direction. So we don't have circular light rays off the equatorial plane, outside of the horizon. This may be different in a plasma. So I've written here again the equations of motion, these 4 equations which we have to discuss. And now we are asking about circular light rays. Yeah, light rays which stay on a circle about the vertical axis, about the z-axis. So they are in particular spherical. So we have again the 2 conditions, capital R is 0, capital R prime is 0. But then they are also what is sometimes called conical. Yeah, so they have to stay on a cone, theta equal constant. And this means the capital theta must be 0. And the capital theta prime, I don't know why this prime looks so funny. It's supposed to be an ordinary prime denoting a derivative. The theta prime of theta is must also be 0. So these 4 equations have to be satisfied. And in the plasma, there are solutions for certain plasma densities. There are solutions with theta different from pi half. And here is an example. So even on Schwarzschild, yeah, there are also examples on Kerr, but I present an example on Schwarzschild. So we are on Schwarzschild spacetime, and we have a plasma density which depends on R and theta. Yeah, otherwise it wouldn't work. So in this case, the denominator of this separability condition is just R squared. And in the numerator, you see we have first a function of R alone and then a function of theta alone. So the separability condition is satisfied. And if you solve these 4 equations, R equals 0, R prime equals 0, theta equals 0, and theta prime equals 0, if you solve this, you find that there are solutions for theta different from pi half. Actually, pi half is a solution, but there are 2 other ones at pi over 4 and 3 pi over 4. And all of them lie at a radius of 4m. So the sphere, on the sphere, R equal 4m, we have 3 circular light rays. So the one in the equatorial plane, that looks quite normal. It's nothing particularly intriguing or surprising. But then we have 2 additional ones off the equatorial plane. So along these light rays, so to speak, the plasma density produces a force. Or actually, it's a theta gradient of the plasma density, which produces a force which balances the gravitational attraction. Yeah. Why is it in vacuum not possible to have circular light rays off the equatorial plane? Because the pull of the gravitational field would drag this light ray away from such a circle. But here there's an additional force in quotation mark, which comes from the theta gradient of the omega p, which is able to balance this. So the light ray stays nicely on this circle. So that's something which we found quite amusing. And with that, I think I stop here. And of course, I'm happy to answer any question you might have.
Okay, thank you for this really nice talk, Volker. Other questions?
Maybe I can ask one. First of all, thank you very much for this very nice talk. So I have a question about these slides. So so there are 3, in this case, there are 3 different circular light rays, but they are on the same sphere.
Yes.
So when you calculate the shadow boundary in this case, do they all contribute to the shadow boundary, and they contribute to the same point?
Yes, actually what I've shown here are only the circular light rays. They are more spherical light rays. And if you take all of them into account, actually you see that the shadow in this case would be a circular disk. And the 3 light rays contribute to this, but they are just 3 points on the boundary of this disk.
Oh, so they correspond to separate points.
Yes.
Oh, okay. Okay. I see.
Other questions? Maybe I have a question then. When we consider the nut case, do you think it might be possible that And I mean, in the normal case, we have just a cone and we have just very specific geodesics on this cone. Do you think it might be different for a plasma?
It will certainly be different, but I don't know in which way it will be different because I haven't made any calculations for light rays in the plasma on the nut spacetime. What you will, well, in the nut spacetime, the vacuum light rays, each individual vacuum light ray stays on a cone. I'm fairly sure this will not be true if you have a plasma. Look, in Schwarzschild, every vacuum light ray is contained in a plane. But if you have a plasma density, then this is no longer true. Yeah, the theta dependence of a plasma density can produce rather wild light rays. And for this reason, I'm fairly sure that if you are on the nut spacetime, then the light rays would not stay on a cone. They would, they could practically do anything you like. If you have a theta dependence, probably they would still be on a cone if you have only an R dependence of the plasma density. That's my guess. I haven't proven this, but I would guess this.
I'm asking because I mean, as you know, I've worked in the metrics, so I was just curious because usually we have these individual cones which are dependent on the constants of motion. And I thought maybe here it could be that for some light rays, at least like which start on a cone, this cone could be a constant for a larger set of the coordinates. That was why I was curious because.
I'm not sure if I understand this. So you're talking about the nut metric, yeah?
Yes.
Okay.
I mean, for the normal nut metric.
Yeah, go ahead.
For the normal nut metric, the cone would be just tilted in any direction and the light rays stay on this cone.
Yes.
And maybe I expressed it wrongly, like what I thought about is like that we have like light rays on the theta cone which move at a constant angle theta. Sorry, I should have rephrased this way.
Yeah, okay. They exist, of course. The vacuum light rays of this kind exist in the nut metric, actually for every opening angle. But as I said, as they are often called conical light rays, probably wouldn't exist at all if for an unspecified plasma density.
Mm-hmm. Are there other questions?
Yeah, I have a question on the plasma term in Hamiltonian. So why you have the subscript P in this omega plasma term?
So you're asking about the very definition of
at
the
very
plasma
beginning
density?
of your talk.
Okay, let me see.
Yeah. The first page, I guess.
Yes,
Yeah.
Yeah, the NXP stands for plasma. The NXP stands for plasma, yeah?
Oh, it's not the conjunct momentum of photon, right?
Oh yeah. I'm sorry. There's so many words which begin with P. Yeah, sorry. No, here P stands for plasma. In the other places it stands for photon. Yeah, sorry.
Okay, fine.
And
another question is my second question is, so from our understanding, so first you have the Maxwell equation and the plasma model, then you can reconstruct the Hamiltonian.
Yes, that's right. Yeah, you do something which is called a high frequency limit. Yeah.
High frequency.
High frequency limit. Yeah, so you make an
optics?
ansatz for the solution of Maxwell's equations in terms of waves, and then you send the frequency of this wave to infinity. Very roughly speaking. Actually, it's a bit tricky for a plasma because you have not only the frequency which is sent to infinity, you have a second parameter. So it's what is employed here is a so-called two-scale method. Yeah, you have another parameter which characterizes how on which scales your background fields change. and you send both parameters to infinity in a way that the quotient is remained constant. Yeah. So this is outlined in great detail in this Breuer-Ehlers paper and also in my book. And yeah, it's a somewhat tricky construction. It is, as far as the basic idea is concerned, quite analogous to the WKB method in quantum mechanics. Yeah, but technically it's more complicated because we have two parameters here, which have to be taken into account.
Okay, I see. Thank you.
Any other questions?
Maybe I can ask one more. So I'm still really confused about could you go back to the last slide with the multiple circular rings? Right. So now suppose we have an observer on the equatorial plane somewhere. So naively, of course, we can the shadow boundary consists of the light rays coming from the one at pi/2 that rings. And I don't understand how the light rays from the other two light rings can also contribute to that shadow boundary of an observer on the equatorial plane.
Well, actually, light rays in this situation are not contained in a plane. Yeah. If you consider vacuum light rays on a Schwarzschild spacetime, each individual light ray on a Schwarzschild spacetime is contained in a plane.
Yes.
But that's not true here, because of the theta dependence of the omega p.
So you mean that the light rays coming from the above and below those two rings can be bent toward the observer?
Yes.
Oh,
yes.
Oh,
and if I remember correctly, this is exactly what happens. Yeah. To be honest, it's a while ago that I did this calculation, but as far as I remember, all three light rays are unstable.
Right.
Yeah, of course, if the other two are stable, but if I remember correctly, they are not. If the other two were stable, then of course they would not contribute to the shadow. Yeah. But as far as I remember, all three are unstable with respect to radial perturbations.
See, this is very cool. And maybe another question. So here you choose a specific omega p, and do you have any idea the criteria for the choice of omega p such that this different light rays could appear?
Yeah, of course. To be honest, when we did examples, Oleg and I, we chose the omega p just in the way that the calculations could be done. Yeah. So we didn't really investigate the question very carefully whether they are realistic or not realistic in view of applications to astrophysics. So, for instance, there are equations. Who wrote this paper? Was it Bardeen? Oh, no, it was Shapiro, I think. Shapiro has, yes, it was Shapiro. He considered the Kerr spacetime, and he considered a dust or even a perfect fluid, being attracted by this black hole, coming in from infinity and falling towards the black hole. Yeah, and he really calculated. I think he even did it with the pressure. He calculated the density which resulted. Yeah, so he assumes that there's a big reservoir, an infinite reservoir at infinity from which this matter is falling in. And then he calculated the resulting density of this matter. And the density, the formula for the density which he found, unfortunately, does not satisfy the separability condition. Yeah, this would of course be a very natural choice for a density, but for this a separability condition is not satisfied. I should say that some other people, not we, but some other people, discussed the light propagation in the plasma numerically for densities which do not satisfy the separability condition. Yeah, you could always do this. You can always do ray tracing in these spacetimes. But we were concentrating on analytical solutions, and for that we need the separation condition.
Well, in my opinion, I think basically this kind of additional light rays or light rings in off equatorial plane light rays they should be more associated with the existence of plasma instead of the separability of geodesic equations, right?
Yes. So as I said, for vacuum light rays, this is not possible.
Yeah.
For Schwarzschild, not at all. And for the Kerr spacetime, not outside of the horizon. Actually, inside the inner horizon, there are two light-like geodesics off the equatorial plane. But who cares about what's going on beyond the horizon?
Thank you very much.
My pleasure.
Are there other questions? If not, I would say we end the official part of the seminar talk here. Thank you very much again for the talk.
My pleasure.